Good morning and welcome to the Monday session of Cisco Live. Hopefully you're here for the 1-2-3 Enterprise Campus Wired Design Fundamentals. I do have to call out one thing because I like to give credit where credit is due. I'm actually the backup speaker for this session. The primary speaker couldn't make it, but I want to give him credit because he's the one that did all the work to create the slides, and that can be quite a task. So slides by Sean Wargo, Principal TME with Cisco, who's focused on wired switching in various aspects for more than 20 years. So I just want to make sure he gets credit for that. So who am I? My name is Scott Hodgdon. I am also a technical marketing engineer at Cisco. I've been here for a little over 21 years now. I did a lot of time on the Cat6K platform, which is still out there here and there. We're not selling so much of them anymore, but I know there's still a bunch out there. I've also worked in the SD Access team now for the last 5 or 6 years. Before Cisco, I was a partner engineer. Before that, I was a customer myself, so I've kind of worn all the relationship hats within the Cisco environment. So that's me. I just want to make sure that we know that this is the abstract for today, right? So we're here to go through this, and primarily we're going to focus on Cisco Catalyst products and primarily on enterprise campus wired design principles. So hopefully this is what you signed up for. And I also want to make sure that we know what this session is not. This is not a deep dive. This is not a CVD review session. We had one of those that was BRK ENS 1500, which took place before this, so can't attend that one now. But you can certainly review it later if you want to when we upload it to the site with everything else. And you can see some other related sessions that we have here. Again, these should show up in the PDF that hopefully you've been able to download, but if not, it should be made available shortly. Another thing, because it is such a big audience, Q&A will be kind of difficult for me to do as we go along. So I'm going to hold Q&A for the end if we have any extra time for that. We have set up a couple of microphones in the aisles here. So as we get to the Q&A, if you want to make your way there, we'll make sure that we kind of go back and forth. I highly, highly recommend that you use the WebEx Teams sign up within the app. Sean is actually monitoring that space as we go through the session. So we have a moderator, maybe even a couple more, to answer questions live. And that space will be available until June 17th. So I'll be monitoring that. Sean will be monitoring that, etc. So again, we'll save Q&A till what time we can use at the end. I won't be doing Q&A as we go along. And you can certainly please use the WebEx Teams within the Cisco event app. Okay, so with that out of the way, let's take a look at the agenda. So what we're going to cover today, again, this is a basics of campus wired design. So we're going to start with the basics. What is a campus? 1, 2, 3, or 4 tier design, right? Because you could have, well, I don't know too many 1-tier designs to be fair, but usually it's 2, 3, or 4. We'll take a look at some high availability technologies that we typically see within the campus, things like StackWise Virtual, ECMP, things of this nature. We'll take a look at some of the new campus architectures that we have, right? Except MPLS, of course, that one's been around for a long time. But EVPN, SD Access, again, where I've worked for the last 5 or 6 years. We'll take a look at those. We'll touch briefly on wireless and security, and then we'll just have a summary at the end. So this is what we're going to cover in today's session. All right. So to start, again, with the basics, what is a campus? So if you want to take the literal definition of a campus, you can see that up here, but it's generally speaking a group of buildings in a geographical location where people and their belongings work together. And really, the campus is usually focused on user access, right? So you look at the Cisco campus, for example, in San Jose is I don't know, 50 buildings or something like this. But I've worked with customers that have just a couple of buildings, maybe a couple of tall skyscrapers, and that certainly would also count as a campus. And I think when we think of campuses, we most often think of something like this. And again, that's Cisco's campus. It's quite an old picture, though. If any of you have ever been to our campus out in San Jose, there's not even the tram line on the street right there. So this was taken quite a while ago. There's no trees or anything like that. But this is kind of what we typically think of as a campus, or a university is often a good example of a campus, or maybe a hospital, with lots of buildings on the ground. So when we think of campus, we usually think of something like this, right? And so there's interconnects between the buildings, usually fiber, your own fiber. And again, you're just aggregating all of those users and those services in those buildings within the network. A campus is not a data center. I know one of Sean's pet peeves is when people talk about campus architectures and they call the distribution layer the aggregation layer, because that's kind of a data center term. And he's been a campus guy for 20 years, so he's like, no, campus is distribution, aggregation is data center. And data center tends to be a little different in a couple of ways. It's usually much more structured cabling like this. It might be usually one big building or just one building where I have a single floor and things of this nature. So there are a little bit of differences between what we would consider a traditional campus and a data center. And as he likes to say, campus networks equal real life, right? Who has this kind of a setup? Yeah, okay. Right, so when I was a customer, we had this kind of setup, unfortunately, because things grow organically, right? Data centers are a lot more structured, a lot more control. Campuses tend to kind of grow organically, so you get the spaghetti of cables that you get to wade through when you're trying to figure something out. Now, Cisco's don't look like this. I can tell you I've been in our wiring closet, so they're a little bit cleaner than this, but I've been in plenty that do look like this. So, yeah, campus is kind of real life. Now, when we talk about campus, we have to look at the pins or places in the network and the topology, right? So we're all kind of familiar with the typical three-tier topology that Cisco has been talking about in their design guidelines and that for as long as I've been a customer. So, I don't know, back in mid-1990s. The three-tier architecture, core, distribution, access. But occasionally you'll see some others pop in here. You'll see a fourth layer pop in. Sometimes we call this the super core or the SP-WAN edge or something like this. And you might also see, kind of an extended access. So if you've got IoT devices or using IE switches or maybe something like Cat3560 CXs to connect conference rooms and things of this nature. So this is kind of an extended access. But this is what we talk about when we talk about places in the network or pins within the campus architecture. And of course, you might also have a collapsed core distribution within that architecture as well. And this really just depends on the size of the organization, right? And sometimes on the size of the countries even, right? As a TME, we're kind of global resources. So I see designs from the US, I see designs from Asia, Europe. Asia and Europe tend to have more collapsed core because most of the countries aren't as big. The US tends to have usually three-tier architectures in most of our customers that I've dealt with anyway. So we're going to talk about each one of these as we go through and how it relates to design and what kind of protocols you might find at that layer, et cetera. Okay? So, first thing we're going to look at is just kind of the multi-layer models I just talked about. And the key here is you always have the three logical layers. Even if I have just 2 layers with a collapsed core and distribution, if I have 4 layers, regardless of how many layers you always have to have at least the 3 logical layers. And those are typically a layer 2 and a layer 3 and then some kind of layer 3 above. So even if you have a collapsed core distribution, you're usually doing layer 2 from the access up there, and then your layer 3 demarcation point, and then layer 3 up. And you're getting all of these other features that you see here within the slide on the right-hand side in those even just 2 layers. But the key is you always have those 3 logical layers, regardless of how many actual physical layers you have. Okay? Sorry, just a quick. The air is very dry here. Okay. The other thing you often look at is modular versus fixed platforms. Now, I came up on the Cat 6K, so I was a modular platform guy. Sean came up on the Cat 6K as well. He's kind of modular platform guy. I've talked to a lot of customers that, they're just absolutely dead set against modular, or they're dead set against stack. It tends to be a little bit of a personal preference. But for us, we don't really care which one you put in these various layers. There are some advantages and disadvantages to each, right? A chassis base tends to have a longer life cycle. It tends to get higher port density. You have the ability to have built-in redundant processors so I can add multiple supervisors into a chassis, things like this. But the downside is they tend to be more expensive. They tend to take longer cycles for development. So if I want to add new features and functionality, that takes longer. They have a slower, they're usually bandwidth limited by the chassis. So there are some downsides, obviously, to a chassis. On the stackable, 1RU switch side, the pros, kind of the opposite of the cons on the chassis side, right? So a little less complex, a little less flexible, however, but usually lower cost. I can kind of add things as I need to as I go along, faster development cycles, but then again, usually lower port density, also lower life cycle than I would have with a chassis, right? There's still some Cat 6Ks out there, I know, that probably we sold in 2002 or 2003. People have changed supervisors over time, changed line cards. It's still the same chassis, still the same power architecture, everything. You just change some of the internals over time, so you have more flexibility. And just out of curiosity, who here still has Cat 6500s in their architecture? Almost gone, he says. Well, that's okay. So a lot less than we used to see. I'd say maybe this was 5% of the people raised their hands. So. But whether you do chassis or not, all of the stuff we'll talk about from a design doesn't really matter because usually you're running the same protocols, and especially on the Cat 9Ks. The Cat 9Ks, whether I have a 9400, which is a chassis, 9600 chassis, 9300 stackable, 9500 1RU, they all run the same code. In some cases, they have very similar, not exactly the same processors and hardware, so I can get the same feature set for the most part out of those. Okay? So when you start to look at the networks from a protocol perspective, you've got your IPv4 suite, and again, usually on the access, you're seeing your layer 2 protocols, your things like 802.1x and these other things from a first hop security perspective, you might move that up to the distribution. You've obviously got some layer 2 running in the distribution if you have a traditional architecture, but that's where my layer 3 DMARC is, so I'm running HSRP or VRRP. I've also then got my routing protocol, my IGP northbound to my core. And then when I get up to the core layer, I've got my IGP southbound. I might have BGP outside or MPLS if I want to act as an MPLS PE at that point. But generally speaking, layer 2 access, layer 2, 3 mix at the distribution, layer 3 full at the core, whether it's V4, V6, it doesn't really matter. There's obviously some scale differences between V4 and V6 on some of the platforms, and that's something to take into consideration. But from a pure protocol perspective, we've pretty much got the compatible versions of everything that you need at each of the layers. And that's unicast. You get into the multicast world. Some people think multicast is just something you add on to unicast, but that's not the case for any of you that have done that. Who is running multicast, just out of curiosity? Yeah, see, it's not that popular, so it was, again, about 5%. But it's its own world, right? I mean, I've got my own neighbor discovery protocols. I've got my own routing protocol, basically. I've got all of these same things that I have for unicast, just for multicast, and then you have to take into account V6 in that. So this is, what we look at from kind of a full protocol stack from multicast perspective and a unicast perspective, V4 and V6, okay? So first thing we're going to look at is the core or / the edge. It might be a SP-WAN edge or something like that. So if you look at the campus core, right, generally speaking, the main goal here is high bandwidth, moving packets around. I'm not going to do a lot of protocols, ACLs, QoS, things like that. I just want to take a packet from somewhere and move it somewhere else really fast. Right now, I guess it depends. And we're going to say things, I think the key word here is going to be tend, right? So tends to be. There's always exceptions, but tends to be these things that we see in most of the designs that we've done with our customers over the years. So again, core tends to be routed. Are there layer 2 cores? Yes. Do you want to do a layer 2 core in a lot of instances? It depends, probably not, especially if it's spanning tree, something like that, because as we all know, spanning tree, if it kind of goes southbound, then that's going to impact everything. So if you can keep that out of the core, that's why we have the multi-tier design, that's better. Tends to use, again, minimal layer 3 features. So again, I don't want to turn on a lot of stuff at the core, even though the hardware is capable of doing all of this at line rate and without any impact to forwarding or performance. I don't really want my core to do that if I can help it. I just want to move packets, right? That's what my core is really there for usually. And so high forwarding scale is what I'm looking for here, and sometimes high density. If you have a collapsed core in distribution where I have to aggregate a lot of access layer, then you might be using a chassis-based system at the core. If I have a core that's just aggregating some distribution layers, I might just have something like a Cat 9500 as a core, which can do 100 gig up and down and has plenty of density. Okay. So sometimes we have these campus core interconnects, and again, this is somewhat rare. You tend to see these in the kind of very large campus environments. You might hear these referred to as a super core or something like that. And this is where I'm aggregating maybe several core layers into another layer. And this tends to be all routing. There's no layer 2 here. And it could even be something, I'll go to the next slide here, like a WAN edge, where I'm now connecting with a lot of VRFs, a lot of more service provider-based type technologies directly into the WAN or into a WAN provider. And so I'm usually going to see a lot of BGP or other types of outside the campus type protocols here, okay? You're going to see a lot of virtualization here usually. Again, the organizations that tend to run these layer 4-tier environments are very large. Airports and large corporation campuses and large universities and lots of those kinds of environments. So from a core perspective, you see a lot of virtualization at this layer typically. And you have to then consider what are the VRF-aware capabilities of the features I want to run at this layer? Because not everything is VRF-aware. So that becomes a factor in determining what I'm going to enable at that layer, or really any layer where I'm running VRFs. Are the features that I want to run also VRF-aware? And again, tends to require highest layer 3 VRF capabilities and feature scale. So that's the core layer, right? High speed tends not to be a lot of features at the, let's say, typical layer 3 core, but if I get into that 4th tier core or SP-WAN edge or something like that, I might be turning on a lot of other capabilities that I wouldn't run in my typical campus environment. All right, so the next thing we're going to look at is distribution. So distribution, usually if I have a large enough environment for distribution, here I'm going to focus on aggregating my access layer and distributing packets around. If I need to go to the core, I can. Whether the distribution layer is passing layer 2 to the core is going to be dependent on what services are required, but typically we want to see layer 2 end here and not get to the core, because if I, again, send layer 2 to the core, then I have some problem with layer 2, I'm going to impact everything. So the distribution layer really gives me the ability not only to set up separate aggregation points for a lot of my access, but it also gives me some protection and kind of siloing of the network apart from everything else in case I do have some layer 2 issue. I won't impact potentially the whole network. All right, so northbound tends to be routed. Traditionally, southbound tends to be layer 2. However, that's somewhat changing, right? I work on SD access, or if you look at other fabric technologies like BGP EVPN, these run on layer 3 routed access layer links, not layer 2. So the world of layer 2 is to the access is kind of changing, and we're seeing more and more layer 3 coming in from the access to the distribution. And which is a good thing, because layer 3 has its own failover mechanisms, and it's much more stable than layer 2, again, getting rid of spanning tree and its potential hazards. So using multiple layer 2 and layer 3 features here, this is where I might now do some feature implementations, so QoS, NetFlow, ACLs, things like that. But that stuff still tends to be more down at the access layer. And from a feature perspective, tends to require medium scale in terms of bandwidth, things of that nature, and then lots of layer 2 and layer 3 feature capabilities. All right. Again, you can have a collapsed core distribution. This is common in smaller environments where you've just got a two-tier network. And again, I'm running the core and the distribution functions now in those two tiers, or in that one tier, I should say, and then the access is separate. So before we said we're not running a lot of features in the core, yes, if I have a separate core, that's the case. But if I'm running a collapsed core and distribution, then I'll be running more features there because now I have to take on that distribution role. So pretty much the same as the distribution from a feature and scale perspective. All right. So we'll get into access now. So access is pretty straightforward, I think. This is where all my users and devices will access the network. And so, okay, that wasn't me. So the main purpose here is just to connect those devices. I'm going to have layer 2 switched north and south usually, although again, we'll look at a couple of the newer architectures briefly that rely more on the layer 3 routed access. We've always had layer 3 routed access, but the challenge with that was typically in a layer 3 routed access environment, I can't have the same subnet in two separate closets, right? I have to have, subnet A over here, subnet B over here, subnet C over here. And so if I have a service that has to go between those, there was no way for me to stretch a subnet between those closets. So I would actually potentially have to run both layer 2 and layer 3, which kind of destroys my purpose for going to layer 3 access usually. And so some of these new technologies like EVPN and SDA and that run layer 3 access have mechanisms in place to get rid of that, and I can now stretch subnets. But typically in an access, if I'm running a traditional layer 2 access, the reason is I want to stretch subnets across closets, across floors, across buildings, et cetera. And so this is where you're going to see all your spanning tree features at this layer. And of course, you'll see them at the distribution layer as well, because I have to have them on the other side. But this is where I typically have my layer 2 capabilities. So again, tend to use multiple L2 features and services, so QoS, ACLs, NetFlow, et cetera. And this is where I'm gathering usually the first bits of information on the flows that come into the network on a port-by-port basis or VLAN by VLAN basis, and sending that information off to my management systems, flow collectors, things like that. Okay? So, tends to require low to medium layer 2 and feature scale. Now, what we've seen more and more over the last many years is this idea of an extended access. So this is where you bring in IoT devices. This is very common in manufacturing and some other verticals where you're bringing in, let's say, industrial Ethernet switches, or in larger campus environments, office building environments, especially going to more of the flexible workspace options. We're seeing more things like small switches in conference rooms running conferencing applications and things like that. So we're seeing more of this extended access where you might be running things like rep or something else. But again, it's still pretty much the same as your traditional access, right? I'm still usually running spanning tree and those related features there. And then I'm aggregating them at the traditional access layer. So we still don't call that access layer an aggregation or a distribution layer because it's not, there's no demarcation of layer 2 and layer 3 there, but you still are aggregating that extended access up to your traditional access. All right, so pretty much very similar to my traditional access, just usually using different devices and in different environments. Again, places like manufacturing and things like that. Okay. All right, so we've looked at kind of the underpinnings and the pins of a campus network and the various layers and what goes on at those layers. Typically, again, what tends to go on there. There's always going to be some variations. But let's take a look at some of the HA capabilities that we've built in here. And that starts with equal cost multipath routing, right? So if you're doing layer 3 access, you're going to have usually 2 uplinks. I'm running a routing protocol. Normally, I'm just going to load balance across those 2 links in hardware. And if one fails, I switch over sub-second normally, and I've got that second resilient link to go. I don't have to worry about any timers like spanning tree, going through learning and all that kind of blocking mode and whatever. ECMP is just all layer 3 done in hardware. So it's based on the routing protocol. You tend to have more neighbors here. You're running the routing protocol on the access layer itself, so you have to make sure that whatever platform you've chosen for that access layer is scalable enough to deal with all the neighbor relationships and all the routes that it might have from around your campus. And it also depends on how you're running your routing protocols. If you're doing, stub areas and things like that, it'll be a little less. But, for ECMP, this is kind of the gold standard, if you will, because no layer 2, and we just use hardware-based mechanisms for forwarding and failover. Now, Ether channel kind of can do this as well, and I can run layer 2 Ether channel, layer 3 Ether channel. But if I just have a single distribution switch upstream, and let's say we're not talking about Stackwise virtual for the moment, then my Ether channel is just to a single member upstream. That might cause some high availability issues if that one member goes offline. Without some technology like VSS or Stackwise virtual at the distribution layer, I can't run an Ether channel to 2 separate chassis. So Ether channel will give you some resilience. It'll give you some additional bandwidth out of that layer. But if you're just connecting it up to, let's say, a traditional distribution layer, then you're really still reliant on that distribution device being available. Now, you could certainly run 2 Ether channels, and that's fine to give you resilience, but then that's a little bit more work. And you're still not relieving yourself of any layer 2 potential mishaps, right? Because I still have to run, if it's a traditional layer 2 access, I'm still running layer 2 across those Ether channels, and then I've got my distribution, HSRP, VRP, whatever, to handle that. And then you've got Stackwise, and this is not Stackwise virtual, this is just Stackwise. So keep in mind, Stackwise is that stacking technology that we've had within the Catalyst family now for quite some time. 3750s, even 2960s can do stacking. Of course, Cat9Ks can do stacking. And this is the ability to represent a single stack of multiple switches as one unit or one access layer entity. Now, you could run stacks of switches at the distribution. You can run stacks of switches at the core, and certainly in some of our smaller customers without massive campus designs, that's fine, right? We've come out with new switches, for example, the Cat9300Xs that can do 100 gig uplinks and 25 gig downlinks and all that, and they can stack, and they can do IPsec, and they can do all these kinds of things. So I could easily run those as a core in a smaller network, stack 2 of them together. I've got stateful switchover. I've got all the same routing protocols. I've got all the same other types of NetFlow, AVC, things like that. And so when we talk about Stackwise, we do usually talk about the access layer, but it's not limited to that, right? You don't have to run a stack just there. And certainly we have a number of customers that are doing stacks at the distribution in the core. Just kind of fit whatever fits you, but typically it will be at the access layer. Now, Stackwise Virtual is a little bit different, right? Stackwise Virtual was really created to simplify the distribution and core layer. Anybody here running VSS or Stackwise Virtual? A lot more hands. Okay, yeah, probably 15, 20%. The main reason we created Stackwise, well, let's go back in history. The main reason we created VSS back in 2008 was to deal with spanning tree issues as more and more real-time and delay-sensitive applications were making their way onto the network, especially voice, right? Voice was very sensitive to spanning tree failovers. Even rapid spanning tree wasn't fast enough to accommodate keeping a voice call up. So we came out with this concept called virtual switching system on the Cat 6Ks. It made its way to the Cat 4Ks. Then we came out with Stackwise Virtual on the Cat 8Ks. And the idea here is I'm taking two physical devices of the same type, and I'm logically binding them together into one unit so that I can run an ether channel from a single access layer to these two separate physical devices, but logically it looks like I'm running an ether channel to one device. And because ether channel failovers happen in hardware, and I don't have to rely on a protocol like spanning tree to accommodate a link failure or something, I had a much faster and much more predictable failover within that what we call multi-chassis ether channel with Stackwise Virtual or VSS. And it was sub-second, right? So as a result, if I wanted to support these delay-sensitive applications, I could now run a VSS at my distribution layer, or now a Stackwise Virtual in the Cat 9K family, and I can make sure that even if I'm still running layer 2 to the access, I'm not putting my environment in danger of dropping delay-sensitive traffic should I just have a simple link failure for some reason. So that's why we created VSS many years ago, and why we've continued to add it, although by another name, in the Cat 3K and Cat 9K families. And if you're wondering, is VSS and Stackwise Virtual the same thing? From a behavior perspective, yes. From a protocol perspective, they're different under the covers, but as far as the way they behave, in terms of failovers and in terms of uplinks from neighbors and things like this, they're identical, right? So you shouldn't, if you're running VSS now and you want to go to Cat 9Ks and you're thinking, oh God, I got to go to Stackwise Virtual, and you understand well the VSS behavior, you already understand the Stackwise Virtual behavior because it's the same, right? There's no difference there. So, same layer 2 and layer 3 protocols here. Again, it still allows us to keep that traditional layer 2 access, but now we can add some resilience in there and some more deterministic behaviors if I run Stackwise Virtual. Now, if I'm running a layer 3 access, I don't need Stackwise Virtual. By the way, I was around when VSS, I was on the Cat 6K team when VSS was created. I'm a big VSS fan where it's used, or where it should be used. But if you have a layer 3 access, you have no reason to run Stackwise Virtual or VSS, because layer 3 access solves the same problem. I don't have layer 2 anymore. I have equal cost multipath. If you just have a few distribution layer switches, you might say, well, I could combine them into one switch, and you know, from a management perspective, that makes things easier. And it does, but I'm a big believer in not running protocols I don't need. Even if they work well, if I don't need Stackwise or VSS because I have layer 3 access, I wouldn't run it. So just keep in mind, the combination of L3 access and VSS/Stackwise Virtual is a little bit overkill. Both of them solve the same problem, okay? So leverages stateful switchover. So if I have these two separate chassis, even though they're one logical unit, they act as if they were one chassis with two supervisors, or a stack with an active and a hot standby. So if my primary supervisor fails in one, or my primary chassis fails, I can statefully switch over to the other again sub-second, and my network continues to run. Now, I'm not going to say it's perfect. I'm not going to say there was never any bugs in this, right? I'm a realist. But the way it's designed and the way it should operate in normal times is that if one fails, then I have stateful switch over to the other, just as I would in a single chassis with two supervisors. So we talked about multi-chassis ether channel. Again, one access layer switch, two layer 2 links, one to each physical member of the Stackwise Virtual pair. If that member fails or the link goes down, I switch over sub-second to the other link, and all of my delay-sensitive traffic should still be forwarding without any interruption. Okay? All right. Now, the other thing, move on here, is again stack-wise, and we talked about this briefly, and I'm just going to build this out here. Stack-wise is just stacking of switches. We've had this for a long time. One thing we don't mention up here that you do get as an advantage these days, and we've had for some time in a stack, is stack power. So if you run Cat 9300s, for example, not the Ls, but the 9300s, in addition to stack-wise, which gives you a bandwidth and stack resilience, with stack power, you can also get power redundancy in there. So the combination of these two things, it's almost kind of like building a little chassis at the Access. Because one of the advantages of chassis, if you remember, is that they have a common power backplane. So if one module or one power module fails, as long as the other power modules have enough available power in them, I can make sure that all of my line cards, PoE devices, whatever, are still getting power. With stack power, it's the same thing. Even though it's separate cables that are connected to each member of the stack, if one power supply in a switch fails and it's the only power supply in that switch, as long as the other power supplies in the stack have enough power to power that switch and its attached PoE devices, it will just continue functioning as if that power supply never failed, right? So when we talk about stack-wise, yes, we have that. That's more of a bandwidth and more of a kind of backplane resilience and ability to add more members. But I also like to talk about stack power, because it adds an additional level of resilience to that environment. And that's kind of critical at the access layer. Because a lot of times, if you have a chassis at the access layer, a lot of times you'll just have one supervisor in there. Whereas with a stack, especially starting with Cat 3Ks, but certainly in the Cat 9Ks, I have stateful switchover here. So in this stack over here, where's my, wrong thing, sorry. So in my stacks over here, if I'm running, stack-wise, and I've joined them all together, the primary switch in the stack, the stack primary, will be the SSO active switch. And then the secondary below it will be the SSO hot standby. And we added this function in stacks with the Cat 3Ks, and we've continued it into the Cat 9Ks. And this is something that we didn't have for all of the history before the Cat 3Ks. And so you're really getting into, when you start adding in power, when you start adding in stack-wise, which is like a backplane, when you start adding in dynamic and default SSO failover capabilities, your stacks start to look more and more like chassis, because each member is essentially a line card. I have a supervisor, if you will, which is the primary member of the stack. I have SSO capabilities. The stacks are starting to become more chassis-like. And so we've started to see those lines blur between, do I care about chassis, do I care about stacks? People kind of are not so dead set on one versus the other these days because of these new capabilities. All right, so with that, we're going to move into the new solutions, or some of the new solutions. One of them's been around for a long time, obviously. But the first one is SDA. So SD Access, or Cisco SD Access, layer 3 underlay, I guess it's layer 3 overlay as well, but you can have layer 2 overlays. And here we're doing what we call a fabric. And a fabric is essentially where I have a layer 3 routed environment, just moving packets from point A to point B. And then I have another protocol, in this case LISP, Locator ID Separation Protocol. It's the one at the top on the blue box there, that's controlling the traffic movement within that fabric. And this is where all my services are added. So the underlay is just layer 3 routed access. The overlay can be layer 2, layer 3. And this is where I add things like virtualization, micro-segmentation, QoS, other capabilities in that overlay. We also have EVPN. So SD Access is a Cisco proprietary technology built on TrustSec, LISP, routing, but all of these things have been around for a long time. TrustSec came out in 2008. LISP came out in roughly the same time. Of course, routing's been around forever. But if you don't want to go with that methodology, which also gives you more orchestration and micro-segmentation in that, but you still want the advantages of a fabric in the campus, I can go to BGP EVPN, which is again another underlay overlay technology where I have the ability to build a layer 3 access and then ride services on top of that via a control plane protocol, in this case BGP. The advantages that these have over something like, say, MPLS, which we have had customers in the past, airports, universities, shopping centers, convention centers, places that have not what I would call multi-tenant in terms of like a service provider, but some of these networks act like service providers, right? You go to an airport and there's all kinds of shops, and you got the baggage folks, and you got the gate agents, and you got the ticket desks, and you've got all this kind of stuff. Well, typically they would run MPLS environments because I would just want to give a VLAN up to a distribution layer, and then from there I put them into a VRF, much like a service provider would, and then send that on and keep that in their own routed space and keep it segmented and secure. But MPLS, we never really had an orchestration for it. It was very hard to manage. If people started moving from one point to the next point to the next point, you had to go and configure all this stuff manually or with scripting if you had it. And it was just a lot of overhead and a lot of manual intervention. So we've had MPLS capabilities in the campus for probably as long as I've been with Cisco, which is about when MPLS came out anyway. And so that's been there. But we're really focused on the newer fabric capabilities in the campus design now because they're more flexible. They're a lot less user intense in terms of having to make changes. And they give you the services that you want with total layer 3 environments, whereas MPLS VPN usually still involved layer 2 to the access. SDA, EVPN, layer 3 to the access, gaining those benefits that we talked about in terms of ECMP, in terms of no spanning tree, things like that. Right? So, quick just side on SD access. So again, layer 3 underlay. I can do layer 2, layer 3 overlays with those handoffs. I've got virtualization, and one of the big benefits of SD access is the ability to have this integrated policy plane, these SGTs. So this is why we kind of focus on SD access as our primary campus solution when it comes to virtualization, because it gives you a more secure, when you talk about zero trust and all that, a more secure environment by doing both network level segmentation with VRFs and micro segmentation with groups using SGTs. All right, and you can see number of overlay layer features there, et cetera. And if you look at the edge is very simple with SD access, and I'll just build this one out as well. But one of the reasons that some customers, especially large customers with large campuses, universities and that, have moved to SD access is in an SD access environment, the access layer is pretty much identical across every edge node. Every edge node will have an identical configuration except for a few IP addresses. Because it's all orchestrated from DNA Center, I don't have to go in and manually make any changes. Everything can be done without any human touching the CLI. And so a university in Australia, for example, had 140 edge nodes for their SD access environment. And one of the selling points was they knew that if they did this, all 140 would be configured identically pretty much. And so from an operations perspective, that was great for them because in the past, they spent so much time troubleshooting little errors that people would make in configuration on the access layer. Users couldn't get in, devices couldn't connect. It was all because somebody fat-fingered a command or put in the wrong IP address or whatever. By going to an orchestrated and automated environment, they got rid of that. Right? So the edge and the access layer of an SD access environment is fully automated and hopefully would reduce a lot of the operational issues that you see around manual configuration. All right, last couple here, wireless LAN. Again, I'll just build this out. Sorry, went too fast there. Whoops, went still too fast. But I think hopefully we've all been familiar with wireless here since this session was focused on wired. I'm not going to spend a ton of time here. But you can see here, the main goal here is to connect wireless endpoints, whether you're doing traditional wireless, where I've got CapWAP riding over the top, and that's an encapsulation, so an overlay itself. Or I'm doing something like Flex Connect, where I drop the traffic right at the switch. Those are usually the two main options there. And then from a firewall perspective, again, I'm aggregating my traffic here. Northbound, I'm going to have sub-interfaces. I'm going to have my trusted and untrusted zones, et cetera. I know I'm going a little fast, but I'm out of time. So that's it. Keep learning. We saw this before. Sorry, let me go back here. So if you did have any questions, please ask those in the app. I apologize we didn't have any time to take questions at the mics, but our 45 minutes is up, and enjoy the rest of the show. Thank you.